Okay, so I'm Fioralba Zacconi at Rutgers University, greeting everyone and thank you for coming to SIAM PDE's webinar. It's my great pleasure to introduce our speaker today, Professor Gunther Uhlmann. Gunther is a Walker Family Endowed Professor of Mathematics at the University of Washington, and also Institute for Advanced Studies, a SIAM professor at the Hong Kong University of Science and Technology. Gunther's research is mainly focused in the theory of inverse problems, where he has made and continues to make seminal contributions. Gunther owns some of the finest results in the field. He has solved many open problems, made connections between various areas of inverse problems, and has posed questions, open questions that have influenced the future research in the field. Gunther has also inspired, taught, and supported generations of researchers in the field of inverse problems around the world. For these fundamental contributions, Gunther is recognized with several prizes, including Böscher Memorial Prize from AMS, Kleiman Prize from SIAM, Birkhoff Prize, which is awarded jointly between AMS and SIAM. He is a member of the American Academy of Art and Sciences, corresponding member of the Chilean Academy of Sciences, a foreign member of the Finnish Academy of Sciences. Gunther is an AMS Fellow, SIAM Fellow, Simon Fellow, Guggenheim Fellow, a Fellow of the Institute of Physics. His work is highly cited and widely appreciated and valued. So we are very happy to have Gunther today, who is going to talk on the Calderon problem 40 years later. So thank you, Gunther, and the floor is yours.
Thank you, Fioralba, for the extremely kind introduction, and to the SIAM activity group in analysis and PD for the kind invitation, especially Anna. So I want to talk about the problem I have been working on and off for 40 years. This is the 40 years later. Also, it's 43 years since Calderon's seminal paper. I'm taking 3 years off because of the pandemic. So this is the problem. Can you determine the electrical conductivity of a medium by making voltage and current measurements at the boundary? Conductivity measures how much current can go from one place to the other. Is the inverse of the resistivity. For instance, blood is very highly conducting and other mediums are much less. And so you put voltage and you measure the induced current flux and you try to infer the conductivity inside. So this is a diffuse type of inverse problems, because the currents indicated by the red arrows in the picture on the top right go everywhere immediately. This is infinite speed of propagation. And so it's very difficult to see where these diffusive currents came from, what is the conductivity that produced those measurements. So it's an ill-posed problem. You can see the pictures here. They don't have high resolution, but it's very good to detect high contrast when there is a very different level of conductivity. For instance, when the blood goes inside the lungs, it's highly conducting, and goes out of the lungs is not. So these type of things. So for instance, Calderon himself, he was an engineer working for the oil company of Argentina in the late 40s, thought about this problem then because of geophysical prospection to find oil, because oil has a very different conductivity than the surrounding rock. So there is a high contrast of conductivity. In fact, the Schlumberger company, the oil company, started with using electrical measurements to detect oil. And in medical imaging, more recently has been proposed for early breast cancer detection as a screening method because the normal breast tissue has a much lower conductivity than cancerous breast tumor. The reason being that blood is very highly conducting and cancer needs blood to grow. Unfortunately, mammography, which is a few X-rays, sometimes misses cancers, and it's very important to detect breast cancer or any kind of cancer early. If you detect breast cancer early, there is a very high chance of complete recovery. This is Calderon, of course, is a famous analyst of the 20th century, has many results to his credit, including Calderon-Sigmund singular integrals, Calderon-Weiland-Kurz theorem, Calderon interpolation theorem, Calderon uniqueness of the Cauchy problem theorem, etc., etc. But he wrote one paper on inverse problems, and this has had a large impact in the field. He said something very interesting when he gave a speech when he received the doctor honoris causa of the Universidad Autónoma de Madrid. Reminiscencia de mi vida matemática, that means reminiscences of my mathematical life. He said in Spanish, I'm translating here, my work at Yacimientos Petrolíferos Fiscales, means YPF, that's the oil company of Argentina. It still exists, was very interesting, but I was not well treated, otherwise I would have stayed there. Was very fortunate for mathematics that this happened. The director of the laboratory where Calderon worked was not happy that Calderon was reading mathematical books on the free time and instead of working on engineering problems. More recently, an application that's being tried out is to imagine a stroke in the brain. It's a difficult problem because of the skull. So there is an inclusion without an inclusion. The skull is an inclusion, difficult to penetrate. But however, we can use electrical measurements to do this. So when there is a stroke, it can be because of low conductivity, that means a clot, so blood doesn't go through. As I mentioned earlier, blood has a very high conductivity, and that's what you can detect. And it can happen the opposite, an hemorrhage. Some of the veins or the arteries burst, and there is a lot of blood, and so a very high conductivity here. But unfortunately, the symptoms are the same in both cases, and one would like to detect quickly, for instance, in an emergency ambulance, which one it is, because the treatment, of course, is completely the opposite in the two cases. And these are simulations that we have done at the moment. This has not been done with real data. These are just numerical simulations, but it seems that it could be a good method for detecting whether it's an hemorrhage or is it a clot. Again, the resolution is not high, as you can see from the pictures, but you want to see which one it is. Is a hemorrhage, like in this case, a lot of blood, or is it a clot? And so we have developed a method which is similar to X-rays. You go around when making electrical measurements, and you can detect which conductivity it is, high conductivity in the right or low conductivity in the middle. And this is a medium with homogeneous conductivity on the left. In hospitals, in some hospitals, this is used for monitoring the functioning of the lungs. A lung can collapse, for instance, especially in these times of COVID, and you can do a continuous monitoring, 24 hours, 7 days, of the functioning of the lungs. You don't want to take the patient to a CT scan or MRI all the time. You can monitor it at bedside. And this can be moved from patient to patient. And it is used in this hospital. And the advantage of this method, which is in the applied literature, is called electrical impedance tomography. It's non-invasive, it's safe, it's portable. As I mentioned, it can be used at the bedside, it can be used all the time, and no serious issues have been detected. It's not ionizing, this is very important, it's very safe, and so on. So this is a COVID patient whose lung function is being monitored at the bedside in this hospital. So let me describe the mathematical problem. So you have by Ohm's law, if the potential is U, I is the current, the conductivity is 1 over gamma. So gamma times the conductivity is the change on the potential, that's Ohm's law. And the conductivity can be isotropic, that is a scalar function, or anisotropic, that is value, matrix value of function, is modeled by a positive definite symmetric matrix. For instance, muscle tissue in the human body is highly anisotropic, and the conductivity is different in the transversal direction and the longitudinal direction. I'm going to talk about that later. And if there are no sources or sinks of current, the divergence of the current, this is the current by Ohm's law, is equal to 0 in the domain. It's a very simple PDE. If gamma is 1, this is just the Laplacian. Divergence of the gradient is the Laplacian. And you impose a voltage potential on the boundary, and you measure the induced current flux. So that's the normal component of the current. How much current goes across here. And this is the information that we have. To a given voltage potential, you assign the induced current flux at the boundary. And the inverse problem, does knowledge of this map determine the conductivity? Of course, this is an idealized situation because you have an infinite number of measurements and so on, but you can solve this question, like in the case of X-rays, you also consider the X-ray transform or the radon transform, which takes infinite measurement. I would like to find a method that approximates the conductivity if you know how to do it for infinite measurements. And lambda gamma is also called the Dirichlet to Neumann map. You send in Dirichlet data to Neumann data. And the difficulty of this problem compared to X-ray tomography, which is the integration of a function along lines in 2 dimensions, is that this is nonlinear because U depends on the conductivity. How it depends on the conductivity is the crux for the inverse problem. That's the difficulties. We don't need just uniqueness and existence and regularity. We need to know more about the dependence on U on gamma. U depends on gamma, so this is non-linear map. And Calderon considered the linearized problem, and he published his paper many years later. And he considered the linearized problem. So he linearized the map going from conductivity to Dirichlet to Neumann map. And he got the following information. This is very quick to do. The data is just the products of gradients of harmonic functions. Remember, at gamma equal to 1, the conductivity equation is the Laplacian. So you are perturbing the conductivity in the direction h from conductivity 1, and the solutions are harmonic functions. So the question is very simple. If you take the products of gradients of harmonic functions, can you recover h? Harmonic functions themselves are not dense. It's an infinite dimensional complement. But the question is whether the products of, in this case, gradients or product of solutions in general are dense in L2, for instance, or L1. So Calderon took very simple solutions, these exponentials, e to the x rho, but these are complex exponentials. So this is a complex vector that has that satisfies rho dot rho is equal to 0. So the Laplacian of U is 0. Minus rho conjugate also satisfies rho conjugate, or rho conjugate is equal to 0. And this means that the length of the real part is equal to the length of the imaginary part, and they are perpendicular to each other. And by taking minus rho conjugate, you cancel the real parts, and you get just information about the imaginary part. So it's a Fourier transform. So you get the Fourier transform of H times the characteristic function of omega in all directions except for 0. But this is an L2 function, so the Fourier transform determines it everywhere. Therefore, you can recover by the Fourier inversion formula H. It's very simple. This is a beautiful, simple paper. It's like 6 pages long. I highly recommend to read it. The next breakthrough came from Conan Vogelius in 1984, and they considered the problem of boundary determination. So the question is, you take a smooth conductivity, what can you recover at the boundary? So they show that you can recover all the derivatives of the conductivity at the boundary. So you can recover, for instance, real analytic conductivities, because you know it at the boundary, all the derivatives, you know it everywhere. And we gave a different proof with John Sylvester, which is to use the fact that this is a pseudo-differential operator of order 1. If gamma is equal to 1 and you are in the upper half plane, this is just the square root of the Laplacian on the boundary. So this is a standard pseudo-differential operator. And in general, it's a pseudo-differential operator. And this is the amplitude. This is the coordinates. Xn equal to 0 is the boundary. So you have coordinates x prime xn, and you can have an expansion of the symbol, homogeneous function of degree 1, 0, and lower order, minus j. And from this, you can recover all the derivatives. For instance, the first term is simply the conductivity at 0 x prime, which is the conductivity at the boundary. These ones recover the normal derivative, and so on. These recover higher derivatives, and so on. So these AJs can recover all the derivatives of the conductivity at the boundary. Okay, so this is the determination at the boundary. The question is, how about the interior determination? So we proved many years ago that if for C2 conductivity, and we will see why C2 is in dimensions 3 or larger, you have the two Dirichlet to Neumann mass having the same measurements, then they are equal. And it has been extended to several different regularities. And the last ones, let me mention, have been by Habermas, which show that derivatives with conductivity that have one derivative in Ln, dimensions 3 and 4, can be uniquely recovered from the Dirichlet to Neumann map, and Calderon Rogers showed the Lipschitz conductivities. But there are several questions here, which is they're still open, whether this is whether this space is optimal in dimension 3 or higher. This nobody has a counterexample for lower, if you know, conductivity that don't have one derivative in some sense. That's an interesting open question. I'm essentially going to talk about 3 dimensions or higher, because that's where most of the open problems are still. In 2 dimensions, the uniqueness has been shown by using quasi-conformal maps by Stahl and Paiverinta to be L infinity conductivities, positive L infinity conductivities. So I'm going to restrict myself to 3 dimensions, which is the physical case in any case. And reconstruction using similar methods to the uniqueness was done by Nachman, and stability, meaning if 2 Dirichlet to Neumann maps are closed, where the conductivities are closed by Alessandrini, this is a logarithmic stability estimate. And numerical methods have been developed using the method that we use, or going to show for uniqueness by several authors in different years. These continue to be of interest. This is a brief summary, some of the results. So why C2 conductivity? So why it has been difficult to improve the regularity? Because the method that has been used is to reduce it to the Schrödinger equation by this transformation. You take U to be square root of gamma times W, then the U satisfies this equation with Q. Now you take two derivatives of the conductivity. So the more singular the conductivity is, the worse behavior of the potential is. But we can consider this problem in more generality for any potential, and this is of interest in scattering. For instance, you take Q minus lambda square, or lambda is fixed, that's fixed energy, and you assign a boundary data and you measure the Dirichlet-Neumann map, the normal derivative. So this is more general, in fact. You solve this problem, you solve this, the conductivity case, except that you need to take two derivatives in some sense. That has been the difficulty here, because even W1 means one derivative, you have to differentiate twice the conductivity. The potential is quite singular. It's in H minus 1. So maybe a different method can give a better, you can improve the regularity and the conductivity, or maybe show that it's not possible to go beyond W1N. That's the open question. And now I use a very simple identity. Q1, U1 is Laplacian U1, Green's theorem. Q2, U2 is Laplacian of U2. You integrate by parts. So the information in the interior is given by information on the boundary. And the left-hand side is linear in the potentials, except that U1 and U2 depend on the potential. These are solutions of the equation. So this is the nonlinear part. This is linear here, and also is linear here. U1 and U2 are not linear functions of the potential, because it depends on the potential. But this relation is linear, and we get, for uniqueness, if this is equal, you get a similar question to what Calderon proposed, but now it's the products of solutions of different equations. Here. One for the Q1 and one for the Q2. So that's the difficulty, and the question is whether the products of those solutions is dense to conclude that Q1 equal Q2. And these are the solutions that one constructs for given potential can be complex value, L infinity, so that rho is equal to 0, rho is equal to 0. That means the length of the real part is equal to the length of the imaginary part, and they are perpendicular. You can find solutions that behave like these exponential solutions for large complex frequencies, for large rho. They behave like Calderon solutions. And how does it go to 0? That depends on the potential. In the L infinity case, is in the L2 sense. But if you have lower regularity, this is in a different space. So these are the waves. Elliptic equations don't have waves, but this is the analog of waves that you're going to probe the medium with. These are the waves. How it can be exponentially growing in some directions, exponentially decaying in some directions, oscillating in others, and so on. And this is used simply in dimensions 3 or higher by taking two of these. So you have three vectors, where in 3 dimensions, so that they are all perpendicular to each other. These are all real vectors. The length of the real part is equal to the length of the imaginary part. And then you have an extra freedom in dimension 3 or higher. You can let this go to infinity. And when you do that, this go to 0. You have the same, you cancel the real parts, cancel the L's. You get the phase of the Fourier transform again. But this goes to 0 as L goes to infinity. And therefore you get the Fourier transform and Q1 equal to Q2. So that has been this called complex geometrical optic solutions. And that has been the main method used for solving this type of elliptic inverse problems. So we have shown that lambda minus lambda q determines q for the Schrödinger equation. That implies in the electrical impedance tomography problem that the indicative normal map of the conductivity determines the conductivity. That can be used also for optical tomography. You send light instead of currents, which is also a very diffuse problem. This is in the diffusion approximation. This is the density of photons of the light. This is the diffusion coefficient. This is the absorption. This is the frequency, which is fixed. And if this frequency is non-zero, the potential is going to be complex value, but you can recover both the real and imaginary part. If omega is zero, then you can only recover one of them. They are both real, so there is no freedom here. You can recover one of them. An optical tomography is used in hospital to monitor the functioning of brain in premature babies. It's good for very small objects because light diffuses rapidly. If it is small, then you can monitor better. And the functioning of the brain. So this is the case. It's very important to do this for premature babies. So for many problems, the probing of the waves is just done by plane waves. You have plane wave solutions. But to localize, when you have partial data, for instance, there are different kinds of waves, nonlinear waves that we constructed with Koenig and Sjostrom, which are complex values also. Tau is a large real parameter, corresponds to model of Rho before. And this is called a limiting Calderon weight. I will explain why in a moment. But one example is the log of x minus x0 when x0 is a point outside the convex hull of the domain. So it's a point outside. And the level sets of these are spheres instead of planes. So you're going to probe the object with spherical waves, complex spherical waves. In 2 dimensions, actually, this is a lot of them. That's why 2 dimensions is easier for this type of problems, because there are many of these solutions. In any harmonic function here satisfies you can use, and this will be the corresponding harmonic function to phi. And it can be constructed explicitly. So these are the solutions. This goes to 0 as tau goes to infinity in some sense, and this is the log of x minus x0 in dimension. We're only going to do dimension 3 or higher. So again, the gradient of the real part is perpendicular to the gradient of the imaginary part, and they are perpendicular to each other. And you can construct the solutions in this case. And the amplitude satisfies a Cauchy-Riemann equation. Because they are perpendicular to each other, there is a plane generated by the gradient phi, gradient psi. So it's like in 2-dimensional Cauchy-Riemann equation. This is called the transport equation, the complex transport equation. This is the conal equation, but it's complex. So this can be used, for instance, to detect inclusions when the conductivity jumps. You want to detect where it jumps and how much it jumps. So this is the point x0 outside, and you can see just with 3 complex waves, you start to detect the shape of the inclusion. And that has been used for many equations, this type of complex spherical waves to detect inclusions, obstacles, etc. With the conductivity, for Helmholtz equation, for elasticity, for Maxwell equations. So now I'm going to consider the more difficult case, which is the anisotropic case. As I mentioned earlier, the conductivity is in this case positive definite symmetric matrix. And the equation is the same, the divergence gamma gradient U, which is written down here. F again is the voltage potential, it's the same problem, and now the induced current flux this has these components, normal components. This is the components of the unit normal, but it's the same, it's the induced current flux and the boundary, and the problem is can you recover the conductivity inside from these measurements. Now this is a matrix. So there are 1/2 n times n plus 1 functions. And there is an invariance to this equation, and you change variables, the equation is unchanged. That means it's of the same type. It will be divergence on some new conductivity and some new potential, but the form of the equation will be the same. So if the change of variables is the identity of the boundary, you will see that there is a new conductivity that gives the same information. So you take a change of variable, which is the identity of the boundary. You take the Jacobian transpose composed with gamma, composed with the Jacobian divided by the determinant, composed with psi inverse. That's called the push forward of this conductivity. Gives exactly the same information. And F is unchanged because the change of variables is the identity of the boundary. So you change variables. You take U, compose psi inverse. You apply the chain rule, and you will see rapidly that this is the case. So there is an infinite dimensional group of transformations that leave the boundary fixed. So this seems to be bad news. It is in some sense bad news, but on the other hand, in practice, we know something a priori about the conductivity. So if this is the only obstruction, we might be able to detect the conductivity uniquely. For instance, in the isotropic case, that we discussed before, if you know the push forward of the conductivity is isotropic, then the change of variable must be the identity. So in that case, you can have uniqueness that we showed before. We have several uniqueness results. But if you have a general conductivity, even isotropic, when you change variables, changes to anisotropic. So you know something a priori about the conductivity, you might be able to detect this change of variables. However, you need to know that this is the only obstruction. And this is an open problem, I will point out in a minute, even if conductivity is smooth. It's not a question of regularity at this point, but it's a question of finding a new method. The method I described before of complex geometrical optics does not work. This is also a geometric problem. For the people who are interested in geometry, you can consider this problem in a compact Riemannian manifold with boundary instead of domain. And this is the Laplace-Beltrami operator, which is the conductivity equation written in geometric terms. So the conductivity is square root of the determinant of G times G upper IJ. This is just harmonic functions. And the Dirichlet-Neumann map is what's called the conormal derivative of U with respect to the metric G. So there is a connection between conductivities and inverses of metrics. The G upper IJ in the standard notation in geometry is the inverse of the metric. So the question is, can you recover the metric inside the manifold by making these measurements on the boundary? It's the same question as I posed before in the case of the domain in Rn for anisotropic conductivity. These problems also arises in holography. Can you realize a three-dimensional manifold in 2 dimensions? And in that terminology, the Dirichlet-Neumann map is called the boundary 2-point function. And it's like the Green's function measured at the boundary. And the problem can be rephrased as, can you recover the bulk from this boundary 2-point function? I can look at this paper of this physicist for the connection with with this holography problem. And the result that is known is only for the analytic case. Even in that case, we can have partial data, but it's all for real analytic boundaries. This is real analytic. The metrics are real analytic. The F is supported here, so this can be a small set. But in that case, we can solve the problem. There is a diffeomorphism, which is the identity of the boundaries. So the identity in the place where the Dirichlet to Neumann map is known, so that one metric is the pullback of the other. And you can recover, you only need to know the boundary and the Dirichlet to Neumann map. You can recover even the manifold itself, I mean the topology, the differential structure, and also the metric inside. But this is a strong assumption that is real analytic. And these are very interesting counterexamples of Daudet, Camran, and Nicolas in 2019. When you have smooth metrics, but in the interior, but they are only hurled up to the boundary, where they have the same Dirichlet to Neumann map, but they're not the pullback of each other. And this is based on, it's exactly the conditions that Miller's counterexamples for unique continuation in the 60s, I believe, have. So Miller constructed examples of functions that vanish at the boundary and the normal derivative vanish, or actually in a part of the boundary where the conductivity is not smooth up to the boundary. It's only C alpha for, it's only hurled up to the boundary, not C1. So, so the question is whether if they are smooth up to the boundaries, are they isometric? Is one the pullback of the other, or the conductivity is the push forward of each other? It's still an open problem. And this if people have any idea how to do this problem, the difficulty from the point of view of complex geometrical optics to construct the solutions of this equation, we need to solve the conal equation. And in the case of the Laplacian, we could solve it, or the scalar case, but not the case, an isotropic case. We don't know how to solve this complex conal equation in general. And this is the difficulty. But the fact that there is non-uniqueness was used for clocking to the fact that the transformations preserve the problem. So the question is, so suppose you have a manifold, an abstract manifold here is like a bell here. This is the idea where it came from. Suppose you pinch all the way. Then if you have information here on this part where the boundary is, you put anything, any information that you want there, you're not going to be able to recover this part, the other part of the boundary, because it's completely disconnected from this. But of course, this is an abstract situation. The question is, can you realize this in Euclidean space? Can you push this example to the Euclidean case? And this is what transformation optics does. You have a transformation squashing a ball to a point. Why do you choose a point? Because a point is invisible in 2 dimensions or higher, in 3 dimensions in particular. You cannot see a point. And the problem is invariant in the transformations. So this is virtual space, physical space. What you want to make invisible is in this ball here. This is where Harry Potter is, represented by this blue fish here. So you squash the ball, you can see when you do this, or you can take this point and expand it to the ball. Then the propagation of light along lines, which is Cartesian coordinates here, deforms by this transformation, and it goes around. And you cannot see this because it corresponds to a point, and the light is reflected, goes around, this becomes invisible. And this is called transformation optics. And you can do this for any equation of mathematical physics There's invariant and the transformations, because the visual space and the physical space can be transformed to each other. And this is the transformation, the precise transformation that we constructed from the ball of radius 1, where the blue fish is. You can put any conductivity here inside, and this is the code, the clock of invisibility, Harry Potter's clock, if you wish. This is the function, and then this is diffeomorphism away from the point, of course. This is singular at the point. And this is the anisotropic conductivity. You can see one eigenvalue is 0. Take the push forward. This is at the code of the clock. It's positive definite. Anything inside, that's the point of clocking. You can put any conductivity positive definite inside here, and you're not going to see it. And this corresponds to metrics that we have seen. And then the theorem is that the measurements you make is exactly the same as the measurements for conductivity 1. We needed to show that you can define the Dirichlet-Neumann map because this is a singular anisotropic conductivity that vanishes at the radius 1, where the boundary is the clock. But you can define it. It's a very simple singularity here. It's what's called conormal type of singularity, and then you can define the Dirichlet-Neumann map. It gives exactly the same measurements of conductivity 1, the same for the metrics. So this is invisibility for the electrostatics, and you can do this for Maxwell equations, for Helmholtz equation, elasticity, many equations. For the conductivity equation, the currents on the left are the conductivity 1. They go in straight lines, of course. The ones we constructed go around. And when you make the measurements outside, it's the same as the picture on the left. So you cannot distinguish the two. You can put any conductivity you want inside here, and you cannot detect it on the boundary. And this is done for simulation. Oh, what happened? The simulation done for Maxwell equations. So this is propagation of plane waves coming in, and you can see it on the other side. It's exactly the same, and you can do this for any direction. It's going to be the same. Okay, so I don't have time to talk about approximate clocking because I only have 15 minutes. The problem is that this is singular at r equal to 1, in the sense that one eigenvalue vanishes first order. Here, the question is, can you get approximate clocking with a non-singular conductivity? And you can. Well, let me mention very briefly. There is the way to do it is by truncation, meaning you take the conductivity very close to the clock, the region you want to clock, the conductivity that works for perfect clocking, and then you put something arbitrarily positive definite symmetric inside. So it is perfectly positive definite symmetric matrix everywhere, called truncation. And then you show that it's not going to be the same as Dirichlet-Neumann map of 1, that's perfect clocking, but approximate, and there's a rate of approximation. So this is good enough for applications. If you want to do invisibility, you can only see up to certain decimal. I mean, this vision is limited, with certain precision. And so this is approximate clocking is good enough. And then there is a method of truncation, and there is a very nice method also. This is the physicist also did something similar. Then instead of blowing up the point to a ball, you just blow a small ball and let the radius of the small go to 0 in this paper of Kohn, Chen, Vogelius, and Weinstein. Okay, so now I will talk about nonlinear equations now. In recent years, there have been several considerations of similar problems to the Calderon problem, but for nonlinear equations. Of course, nonlinear equations appear in many applications. In several resistors are nonlinear, depend on the conductivity or the gradient or both. And so it's natural to consider nonlinear equations. So the problem is already nonlinear, but now the additional difficulty is that the equation is, the coefficient depends nonlinearly on the solution, can depend on u and the gradient of u. And the idea is that, in fact, the fact that the equation is nonlinear actually helps rather than hinders. In general, you have a nonlinear equation, you expect not to get as good results, but for inverse problems, it's the opposite. The fact that there is more interaction of waves helps. And this was realized in the hyperbolic case for the wave equation with nonlinear quadratic terms in this paper. We did multiple linearization, meaning we look at the interactions of multiple waves, and this was done in the elliptic case here. So there have been previous results about the conductivity that I mentioned here, depending on different conditions. Okay, so let me explain first the semilinear case. So let's take a potential that depends on the power of the solution. And Q has some regularity. And in this case, for a small enough data, you have a unique solution of the Dirichlet problem, and you can define the Dirichlet-Neumann map. And you can consider even the case of partial data, which is an open problem for the linear case. So you take the support in some open set, and you measure the normal derivative in some other open set. It could be the same. And the theorem is that in this case, the measurements determine uniquely the potential for this equation. This is unknown in the case of the potential, in the case m equal to 0. You take the potential, this partial data problem is unknown in dimension 3 or larger. Even if gamma 1 is equal to gamma 2, is unknown. There are some partial results, but the general result is not known. And you can consider more general semilinear equations as long as depends holomorphically here. That means it has a power series in U, starting with U squared. So it's really nonlinear. So V at 0 is, and the derivative of the linear term is 0. So start with U squared. And in this case, the same proof gives this more general result. The potentials are the same for semilinear equation. And the idea is to do let me just do the case m equal to 2. For simplicity, you can do any case, and the potential case is similar. But let me explain the simplest case, when you have a quadratic nonlinearity here. And in this case, we take two parameters. We're going to look at second order linearization, epsilon1 and epsilon2, which are going to be small. And we differentiate with respect to epsilon1 and epsilon2. And what you get is something similar to what we had before. So this is the second order linearization. Q1 minus Q2 is orthogonal to the products of three solutions, but these are just harmonic because you are linearizing around 0. Because of the assumption that starts with a quadratic term here. So this is similar to what Calderon had done, but except for the case that the support of the harmonic functions is contained in an open set. Remember, it's partial data. The support of the function is here, it's 0 here, it's grounded on this side, and you measure it on the normal derivative in the other open set. And this was done by, we show with Dos Santos Ferreira and Koenig and Sjostran that the span in this case, when you have harmonic function that vanish and the complement of any open set is dense. So now you have a lot of this. You have the product, you can take anything you want here, essentially, of this. And then you conclude that Q1 is equal to Q2. So, but here you're doing the linearization, second order linearization at 0. So the question of products or solutions, it comes up all the time in this type of problems. And we also did this for the conductivity question for Calderon's original problem, where the conductivity depends on U and the gradient of U. There have been some partial results previously when you have dependence only on U, or when it doesn't depend on U, depends on the gradient of U and so on. But this is the general result. Again, we assume you have power type of nonlinearities. It's holomorphic in U and the gradient U. No other condition except for smoothness. And this is the Dirichlet-Neumann map in this case. And the result is that in this case, and you didn't need sufficiently small data, then you can recover the conductivity uniquely. And in this case, I don't have much time to explain the details of the proof, but it's just multiple linearization. So you expand in Taylor series in U and gradient U, call it lambda here. So you need to recover all these derivatives here. So it's the case differential, and you get a complicated expansion. But these are the terms that you need to prove that they are the same. All the derivatives in the directions of U and the gradient U at 0 to prove that these terms are the same. And this again reduces to a question of span of solutions. You get some, I will explain the case of just in the case of second order linearization. Again, you get a tensor, you get solutions. It's more complicated. But in the case m equal to 1, it's just the products of gradients of solutions of the conductivity equation. In the more general case, you have to work harder, but it's essentially the same idea. So again, the question of products or solutions of equations is crucial. And let me just, I'm not going to look at that. Let me finally talk a little bit. I have only 5 minutes about other type of Calderon type of inverse problem, which is for non-local operators. The fractional Laplacian, this is non-local, you don't preserve support. This, even if U has compact support, this doesn't have compact support. And so this involves values of U far away from X. This fact that it's non-local it complicates many things about the direct problem, but helps for the inverse problem. Of course, this fractional Laplacian test appears in diffusion, different models of diffusion. But this is a super diffusion, Levy flight in probability theory. But in any case where there are long-range interactions, you get non-local operators here. And so the analog of the Calderon problem in this case is you have a potential, you have the fractional operator, and we don't consider boundary data. We cannot consider this is non-local, but we look at the exterior. So the Dirichlet-Neumann maps is just a fractional Laplacian restricted to the exterior or an open subset of the exterior, as we're going to see. Because it's shown that as S goes to 1, you're approximating the local problem, this goes to the normal derivative. So this is the analog of the Dirichlet-Neumann map. And the inverse problem is knowing this operator associated to this non-local equation now, can you recover the potential? And the theorem is, in fact, you do, and you can have any open you can make measurements any open subset of the exterior, and measuring any other open set, and be as small as you want, then you get the Q1 equal to Q2. So this is arbitrary open sets, and the method works in any dimension. So since I'm running out of time, let me just say that the main difference with the local problems, you get the same type of identity that the product of solutions now for this non-local case is orthogonal to Q1 minus Q2. But the difference now is that any function can be approximated by solutions of the fractional equation. That's the main new insight. You don't need complex geometrical optic solutions, which complicate things, because you can approximate any function by this solution. So here you can take U2 to be anything, U1 to be anything. So Q1 minus Q2 will be orthogonal to any function, therefore Q1 equal to Q2. And this has implication for the anisotropic problem. So let me mention this result, very nice result of Ghosh, Lin, and Xiao, where they took the anisotropic conductivity equation. And in that case, you can recover that plus a potential, although this variable coefficient, we cannot do this in the local problem. You can do this in the fractional case, when you have the fractional elliptic equation, because of this Runge type of approximation. This Runge type of approximation, which you had to prove for this more complicated equation. They consider the Laplace-Beltrami or the conductivity equation to some power. So the fact that you have non-locality helps. So the moral of these two last examples, the non-linearity helps, and the non-locality also helps for inverse problem. Thank you.
Thank you very much, Gunther, for this very nice overview of such an important problem in inverse problem, sorry. So it's open for questions. So any questions for the audience, from the audience?
No, nobody understood anything?
So is it any questions? Maybe I could ask one and then maybe start it. So, for the non-uniqueness in R3, so what do you think? What is your conjecture? So
for the anisotropic problem,
yes,
or for the isotropic?
Yeah. So there is this example, right, which is still open whether they are connected via a transformation optics.
Oh, this one,
so what do you think?
The anisotropic or the
yes.
isotropic?
Yes, anisotropic.
Anisotropic. Oh, my conjecture is that it's true for smooth conductivities. Yes. The reason, because in that case, unique continuation is valid from the boundary. So if U and the normal derivative vanishes an open set, if the conductivity or the metric is smooth up to the boundary, then it's zero. The solution must be zero. There is a connection with unique continuation. It's not a theorem, because we don't know how to connect the two problems directly, but intuitively there is some connection. And so I believe the result should be true, but this is, I have offered, I don't have $1 million that the Clay Foundation does, but I have offered $1,000 to anyone who can solve this problem. somebody asked me whether it's for every dimension, for every dimension, 3, 4, and so on, 1,000 for each dimension. No, it's 1,000 for all the dimensions.
Right, from 3, yeah. Okay.
From 3. For 2 dimensions, it's known. Because in this case, 2 dimensions is simpler. Some things are simpler, some things are more difficult. So in 2 dimensions, this problem is simpler because you have isothermal coordinates.
Yes. Yes.
You can transform the anisotropic equation to isotropic. So that makes the problem much easier in 2 dimensions. That's not true in dimension 3 or higher.
So this counterexample is Hölder up to the boundary. So
Hölder up to the boundary uses very directly these counterexamples. It's based directly on this counterexample. Very nice observation.
And you believe that these 2, G1 and G2, are not related via transformation optics?
Well, in this case, they are not.
It's not proven though, is it? It's proven. Oh, okay, okay.
It's proven. No, it's proven.
Okay, I did. Okay. Mm-hmm.
Yeah, these are the samples constructed here.
Okay. Mm-hmm.
Yeah.
Thank you.
But if it is smooth, I believe that they should be connected by a transformation.
Mm-hmm. So any questions? Any other questions?
Was too fast?
No.
Yeah.
For the nonlinear, I understand that the smallness of the data is bounded. It's by the. I mean, to determine, you need the existence of solutions in order to determine the define the Dirichlet-Neumann operator.
Right.
You think would be any way sort of around that? I mean, for wave problems, it's sort of for conductivity. Maybe it's okay because you apply a very weak current, right? But for
you apply very small voltages or currents.
Yes, or voltage, yes. But for the waves, probably.
Yes. No. That's a valid question. And for some equations, global. The question is whether you have a global existence of solutions. So, scattering type of situations. And in that case, it is a very valid question, larger data because of waves and interaction of waves. And there has been some work in that direction, a strong interaction of waves, for instance, in relativity. The names escape me right now. Rodiansky and some co-authors have considered interaction of strong gravitational waves. But that is a very valid question. In the case that you have global solutions, as you have sometimes, some equations you don't, or some equations you don't know, like the Navier-Stokes. But in that case, you want to consider strong, not just small data, but larger data. Yes.
There are 2 other questions. Yes, thank you, Gunther. Valerie, please unmute yourself, please. Yes.
Hello.
Yes.
Hello.
Oh, okay. Connected. Can you hear me?
Yes.
Oh, right. So on your latest remarks that first nonlinearity helps and then non-locality helps, right? And implication is that the easiest situation is when you have nonlinear, non-local models.
Right. Yes.
When you have both, is it something you have considered?
You have what?
When you have both nonlinearity and non-locality simultaneously.
Yes. There has been several. I didn't mention all the. This is a very active area right now. There are several papers considering that semi-linear, for instance, and non-local. Yeah, there are, yeah, but both are
most helpful combination. It is right.
Combination though that has been considered for some situations, not the general situation.
Right.
Also, another interesting question will be the case of where you have not the fractional Laplacian, but more general non-local operators.
Mhm. Right.
Yeah.
Right.
One case that has been considered the Boltzmann equation. And so this, I just gave some of the basic examples, but there have been many results. I did not. For instance, for nonlinear elliptic, there are all these results, and not being. I mean, these are not all for the fractional Laplacian. There are many papers also. So you know, the question you consider has been, in some cases, not a general case.
Right. Thank you.
Sure.
There is another question by Salim. So please unmute yourself. Hello. Salim, are you there?
Yes,
Yes.
I am. Yes. Have homogenization techniques been used in studying the anisotropic case?
For the inverse problem?
Yes.
Not directly, but it has been used for the clocking problem, because the question. So here the conductivity is. There are two issues here with this construction to get some practical applications. Is that first of all, I already mentioned this is degenerate r equal to 1, the eigenvalue is 0. There has been, there's several works on approximate clocking, but it still is anisotropic, and that's difficult to realize for materials. You want to construct materials that have this conductivity or these electromagnetic parameters. So the question is can you find an isotropic model for this anisotropic? It's the inverse homogenization in some sense. In homogenization, you look at small scale, you get anisotropic from isotropic. Want to do the opposite. And it has been done. So there is a paper that I wrote with Urilev and Razas, where we construct isotropic conductivities or isotropic electromagnetic parameters for Maxwell equations that approximate, that give you approximate clocking. So it's the inverse homogenization. So you want to go from anisotropic to isotropic. But what you're asking is an interesting question, whether one can use it for the problem, for the anisotropic problem, where one can use homogenization. That I don't know, and I haven't seen work in that direction to solve this problem. That's the question, right?
Yes.
Yes.
Thank you.
That will be very interesting, but I don't know how. Question for you.
No, for other colleagues.
For other colleagues, yes, please. The idea of this lecture is to encourage people to work on these problems, which need new ideas.